Hello and welcome to another mathematics video in which we seek to analyse and solve ordinary differential equations, mainly anyway. On the screen, you'll see a simple non-linear circuit. It's an electrical circuit with a voltage source E, which is a function of time, a non-linear device which has voltage Ki squared and an inductor L. And of course, you can turn the circuit on and off via this switch. Now, the question asks us to deduce or find a non-linear ordinary differential equation for the following electrical circuit. Now, what we're going to do is we're going to write down the overall voltage of the entire circuit. So we start with the fact that we've got E of t, which is basically the voltage here on the left-hand part of the circuit. So we're going to write down that E of t is equal to the voltage flowing. Well, the voltage across the inductor is L times di by dt. And then, of course, we've got this voltage of this non-linear device, which we just simply add on as Ki squared. Okay? So that is a differential equation that describes the circuitry in this circuit, basically, in what we've drawn here on the right hand side. Now, we'll just say, for the sake of argument, suppose that the voltage source is E of t is equal to 10 volts. Then what we have is L di by dt plus Ki squared equal to 10, right? And what we're going to do now is first of all, we're going to cut and paste this equation, and we're going to have a go at solving it. So basically, we divide throughout. Let me just click on the black ink. So divide throughout by L to get di by dt plus Ki squared divided by L equal to 10 divided by L. Oh, and let's give these equations some labels. So we'll call that equation 1 and that equation 2, right? So now what we want to do is move this to the other side of equation 2 so that we get di by dt on the left, and that's equal to 10 over L minus Ki squared over L. And we'll call that equation 3. We can actually rewrite equation 3 as di by dt equal to K over L times 10 over K minus I squared, right? So we've just simplified the bit in brackets because we ideally don't want a coefficient in front of the I squared. We just want to leave that as a coefficient of 1, for example. It just makes the uh, resulting algebra, or rather the forthcoming algebra, easier. So let's cut and paste equation 4. Right, okay. So what we can do is now separate the variables. So what do we get? Well, if we separate the variables, we'll just write that down. Separate the variables. To get di over 10 over k minus I squared. Oh, and we want integral signs in there as well. And that's equal to k over L times the integral of dt. Right? So we'll call that equation 5. I'm just going to write equation 5 as di divided by the square root of 10 over k all squared minus I squared. And that's equal to k over L dt. So that's equation 6. Right. The reason why I've written the left-hand side of equation 6 like this, with the root of 10 over k all squared, is because it makes it easy to work out what our substitution has to be, because that's what we're going to do next. We're going to use a substitution for I to simplify the expression and therefore integrate it easier than we would have otherwise done. So let's cut and paste that and move on to another page. So where's my nib gone? There we are. Okay. Right. So for this, or rather to solve this equation, we use a substitution. I'll write this in green. Use the substitution I equals the square root of 10 over k tan, so it's the hyperbolic tangent of theta. So differentiating both sides of that, we get di is equal to the square root of 10 over k hyperbolic secant squared theta d theta. And also we can rewrite the original substitution, I equals the square root of 10 over k tan theta, to give well, if we multiply both sides by root of k and divide both sides by root 10, then we have tan theta. And then, of course, taking inverse hyperbolic tangent functions of both sides, we have that. So we'll need that in a little while. So equation 6 becomes I'll write this down. Equation 6 becomes the integral of, well, we know what di is. Di is this term here. Excuse me. So we've got the root of 10 over k, sec squared theta d theta, divided by, and I'll just get rid of this stylus, divided by the square root of 10 over k, all squared, minus, and well, I is root of 10 over k tan theta, so we're squaring both sides of that, or rather we're squaring the right hand side to give the square root of 10 over k all squared tan squared theta, and that's equal to k over L times the integral of dt. And what I'm going to do is, I haven't made the integral sign on this side particularly clear, so let's just write that in. There we are. Okay. Now, if we go on to the next page, what I'm going to do is I'm going to cut and paste that as well, and add to new page. Right, okay. So this can be simplified to give, well, we can take this term outside the brackets, outside the integral sign, and we can take this term and this term outside the integral sign. So what we get is, I'll write this in green, and then hopefully I won't make any mistakes. So we've got 10, the root of 10 over k, all divided by, well, now that we're taking this and this outside the brackets, we can simplify those to just give 10 over k, like so. And then times the integral of sec squared theta d theta over 1 minus tan squared theta, and that's equal to k over L times the integral of dt. Now, where did we get to? Well, we got to equation 6 up here, so we'll call this equation 7 and this equation 8, okay? Now we know that 1 minus tan squared theta is equal to sec squared theta, right? It's just a trigonometric identity. So what we now write down, if we rewrite equation 8 as, well, we've got, we can multiply, first of all, both sides by 10 over k, leaving on the left-hand side the root of 10 over k times sec squared theta d theta, all divided by sec squared theta, and that's equal to 10 over k times k over L, right? Times the integral of dt, and that is equation 9. So we'll just cut and paste that again, So now you can see that the sec squared thetas disappear, leaving a simplified form of root of 10 over k times the integral of d theta equal to 10 over L times the integral of dt. And we'll add on our constant of integration now. So what we get if we integrate both sides of this equation is the root of 10 over k theta equal to 10 over LT. Oh, and of course the C, we've already added that in, so we just leave it as plus C there. So that is equation 10. Now we can multiply both sides of this equation by the root of k divided by 10 to give theta equals 10 over L times the root of k over 10 times t plus c times the root of k over 10. And we call that equation 11. Right, so let's just cut and paste 11, equation 11. Right, so we can simplify equation 11 if we wish. So that gives us theta equals well, in actual fact, I'm going to bring the k over the root of k over 10 outside the brackets to give the root of k over 10 times, in brackets, 10 over L times t plus c. Right, like that. Now we know, oh, let's give that a label of equation 12. Now, writing in green again, we know that theta is equal to, well, what is theta equal to? Well, if we go back, we already deduced that theta was equal to the inverse tan of I root k over root 10. So what I'm going to do is, well, I'm going to have to try and remember that. So theta equals, let me get green, so theta equals tan to minus 1 of I, and we'll just write this as k over, or the square root of k over 10. So we have, we'll write this in black, tan, I should say the inverse hyperbolic tangent of I root k over 10, and that's equal to the root of k over 10 times, in brackets, 10 over L times t plus c. And we call that equation 13. Right, so now what I'm going to do is cut and paste that equation. Right, so we can simplify it a bit more. So leaving the I root k over 10 on the left hand side, what we're effectively doing here is, I'll just explain this a little more clearly. we've got an inverse hyperbolic tangent function. So we want to get rid of that and just leave the bit in brackets on the left-hand side. So what do? Well, we take the hyperbolic tangent of both sides of equation 13. So I times k over 10. Let's just put a red bracket around that, black again, and that's equal to tan hyperbolic tangent of in brackets. Let's see if we can squeeze this in. Root of k over 10 times 10 over L times T plus C. We'll call that equation 12, right? So taking the hyperbolic tangent of an inverse hyperbolic tangent function just leaves I root k over 10, and that's equal to the hyperbolic tangent function, or than, as I've been calling it, of, in brackets, k over 10 times, in brackets, 10 over L times T plus C. Close brackets and close the big bracket, and that is equation. Oh, what have I been doing? Well, that was equation 13. So in actual fact, I've mislabeled this equation, haven't I? So that should be, where's my pen? There we are. So that should be equation 14, and this should be, oops, let's just, let me just get my eraser on that. Right, there we are. So now, if I can get my pointer back, that becomes equation 15. Right, little error there, but never mind. Now we can simplify this equation a bit more. I'll just cut and paste that so that I can easily reference the equation and hopefully not make any mistakes. So basically the current I, let me move down the page a little more. So I is equal to, if we multiply both sides by the square root of 10 over k, we get just I on the left hand side, and we're left with the square root of 10 over k than of, and in brackets, k over 10 times 10 over L T plus C. You could actually simplify that further. So in actual fact, you could take the 10, where's my pointer? You could take this outside the brackets. So what you're left with there is 10 over L times T plus L over 10 times C. So this is perhaps a little tidier. So we've got I equals the square root of, it's a bit of a squiffy square root sign. So I is equal to the square root of 10 over k than of Well, how can we simplify this? Well, we've got a root 10 on the bottom and a 10 on the top. So that would become square root of 10k, right? Over, well, we could have it as the square root of 10k over the square root of L squared times t plus L over 10c, right? Whoops. Let's make that look a bit neater if I can. So is that right? We brought a root 10 to the top, so it becomes 10 times 10 to the minus a half, which leaves you with square root of 10. Square root of 10 times the square root of k is just the square root of the whole of 10k. And then on the bottom, we've just got an L on its own, but I've called it the square root of L squared. So let's tidy that up a little more. And yeah, I'll put it there like that. So now I is equal to 10 over k hyperbolic tangent of in brackets square root of 10k over L squared times t plus L over 10c, right? And I think that becomes equation 16. And that is the solution to the original equation, which was, and we'll just write it down, is, let's write it in green. This is the solution to L di by dt plus ki squared equals 10. And there you are. That is that, as they say. So again, I hope you've enjoyed that, gained something from this mathematics lecture, and that you will come back, watch more of my videos, and until then, I'll bid you farewell for now and see you soon. Okay, take care.